Alright guys, I'm going to walk you through your homework problems that are due tomorrow. So just to refresh, all four of the problems are solving for friction. Each one of them is giving you a different amount of knowns and different types of known values. So this is page 141 in your textbook, and we need to have 1 through 4 done by tomorrow. Go away. Minutes. Oh my God. Okay, so the forces or the equations that need to be on your note card is you need to have the summation of the forces equal to mass times acceleration. So remember, this is Newton's second law. Another way of writing this is that the force net is equal to the mass times acceleration. Remember that force and acceleration are both vector quantities. Therefore, the direction matters. Okay, anytime you have a vector, you're going to need to resolve it down to the x and the y axis. So if it doesn't already naturally fit with 90 degrees with one another, you have to put it onto one of the axes that are 90 degrees from one another. So you can rewrite it on your equation sheet or your note card like this if you would like. You can do the summation of the forces in the x is equal to the mass times the acceleration in the x, and the summation of the forces in the y is equal to mass times acceleration in the y. Remember that Greek symbol that looks kind of like a funky 3 is sigma, and that means the summation of. If you get overwhelmed by that, you can use force net, like I wrote up here, so capital F subscript net on your note card if you have a hard time with that one. Remember, throwing a bar above them is an easy way to remind yourself that those are vector quantities, so we have to use those a little differently. The other equation you're going to need for sure is your friction equation. Remember, the equation's the same. Friction's just equal to the force normal times mu, but there's two types of frictional forces. There's kinetic friction and there's static friction. So kinetic means that it's in motion. So kinetic friction and static friction. So static, think still. Kinetic, that one's in motion, like kinetic stretches versus static stretches. Now, another equation, I tend to just expect you to know this, so if you don't, do put it on your note card. Force weight of any object on Earth is equal to mass times our acceleration due to gravity. And the accepted value for gravity that we use is 9.81 meters per second squared. Again, remember, it's acting down, so when you use it, you put the negative in, but the force itself, we'll say, is 9.81 meters per second squared. Alright, so if you don't have those, make sure they're there. Now I've got 3 different situations outlined on how the force normal can be a little bit different. That seems to be what's throwing us for the most part when we're setting up our problem and understanding how it can be different. I suppose there's another one where there's other forces at play, which I could show you too, but this is the most basic situation. Situation 1 is where you just have force weight acting down, right? Force weight is always going to act straight down. Okay, force weight is always going to be going to the center of the Earth. That's the goal of gravity. Now, force normal is going to be perpendicular to the applied surface. So whatever 2 contacting surfaces you're referring to, it's going to be perpendicular, which means at a 90-degree angle to that surface. So here, this is just sitting, therefore force normal is the most basic it can be. It's straight up. Okay, that situation when there's no other forces acting on it is when these 2 can be equal and opposite. That means is your force normal in this situation only is force normal and force weight equal to one another. And that's because there are no other forces at play in the y direction. And it's not moving in the y. Now, situation 2, this is like if you have a book on the wall and you're trying to push it against the wall to keep it there. You've got a force push, pushing it against the wall, and the wall is actually pushing back on you. Now that push back on the wall is your force normal. Okay, so your force normal is going to be whatever you're pushing, it'll push back. Now that's not the only reason it's staying up. There should also be a frictional force that's keeping the book from sliding down a little bit, and that's static friction again if we're assuming it's not moving. And force weight, as always, is acting down. So notice how this time force weight and force normal are even perpendicular to one another. So in reality, that force normal really has nothing to do with force weight. It's just in our most basic situation, it's going to be the same. Now here's an example that has been thrown us currently, and I think it's because we just get a little overwhelmed with all the information, but just take it one step at a time. Okay, if you go one step at a time and simplify your diagrams when you can, it'll be just as simple as these ones are. Just make sure you don't forget any forces acting on your object. Okay, so this one, you've got your force weight acting straight down, but you're at a 45-degree incline. So what that means is that your force weight is actually 45 degrees off of your y-axis. So think about it, when you're like this, your force weight's down, straight down. But if you were to turn it to a 45-degree angle, your force weight is 45 degrees off that axis. So again, let me show that. So let's say that you're flat. Let's pretend that the box was flat. If it was sitting right on the flat surface, force weight is this pencil acting down, and this is my x-axis. If I were to turn my x-axis, however much I turn it, that's how much my force weight turns too. Okay, so again, however much I turn my axis, that's how much my force weight is turning off of the x. That's why this is a 45, because this one went 45 degrees up. So my force weight to that axis is 45 degrees. Alright, so now that is that situation. Okay, now there's maybe a fourth I should mention, and it's very similar to this one, but let's pretend that you have a box sitting on the floor. Alright, and you obviously have force weight acting down. I'm going to say that the force weight is 3 blocks down. Okay, I'm going to try to give some like arbitrary quantities so you can get some idea for perspective on this one. So force weight's acting down. Okay, so 1, 2, 3, 4. The block is not moving. Okay, so 1, 2, 3. So 3 past the block. So 1, 2, 3. I know if it's not moving, my net force up here has to get up to there. But let's say that you have a string attached to it and you're pulling with a force up to here. So that's like a force pull. What's going to happen is the force normal is still perpendicular to these two surfaces interacting, but it's only going to be whatever that extra bit needs to be for it to stay not moving. Okay, that force normal is not going to give any more than it needs to. Alright, so that would be maybe the fourth example we could say of how things can get a little bit different. Alright, so with all of this considered, let's go ahead and try one of our problems. Again, we're on page 141, and I'm going to do 1 through 4. Hopefully with the video recording, you actually have the ability to pause me and take your time to do your problem. Alright, I'm going to try not make this video last forever here, so let's look at number 1. Number 1 says a student pulls on a rope attached to a box of books and moves the box down the hall. Student pulls with a force of 185, so let's make sure we got our given information or our knowns. We know that the force pull is 185 newtons at an angle, at 25 degrees. 25 degrees. 25.0, just so we remember sig figs here. In the box mass, so mass is equal to 35.0 kilograms, and the mu k as it is moving is 0.27. Alright, I've got my given information jotted. Now I'm going to go ahead and write. So again, this is number 1, page 141 in your physical textbook. 1 through 4 is what was assigned. Again, these are your friction problems. Alright, so number 1, let's draw a picture. The hallway is flat. They made this one easy for us. If you tried jumping right into number 2, you probably were a little confused. Alright, a box. There is a rope attached. I'm going to just start with the rope attached to the center of mass to make it easier. And a force pull of 185 newtons. And my theta is 25 degrees. Now I can't do anything with that because it is not a force vector in the direction of my motion, because I know that my motion, my box, is moving that way, so that has to be one of my axes. Let's make it our x. That's the easiest way to do it. They want us to find acceleration, but I know that it's being accelerated in the direction it's being pulled. Alright, so the other forces acting on this object are going to be force weight, force normal perpendicular to the surface that's interacting. Alright, and I know that this plus all of this are going to be the same. But I'll pull it down so you guys can see that a little bit better. How about that? We'll pull the tip of the arrow to 1, 2, 3 blocks down. I went 1, 2. I'm going to try to make these angles equal. This really is in the middle, it should be. Okay, and then 1, 2. So I'm going to add one more up, and that little extra bit that it needs to go to be equal, call my force pull. Now I don't know that these are necessarily how it's panning out. Like, I don't know that the force normal is bigger than the force pull yet, but we'll have to see here. And then my force pull in the x. Obviously my y is technically here, that's my force pull in the y, where I'm going to be solving for it, but I'm going to tell you that it's going to be acting up, obviously, right? You pulled over and up, so that's your up, this is your over. Your over can only apply to it moving this way, and your up can only apply to these forces. Now, based on what the problem is saying, what I know about my x and my y is that the box is accelerating the x and not moving in the y. So when I go to sum my forces in the y, oh boy, forces in the y, and set it equal to mass times the acceleration in the y, what I'm going to notice is if that is 0, then I'm setting it equal to 0. Okay, anytime it's not moving in a direction, then it's definitely not accelerating. Okay, if it's moving at a constant velocity, also not accelerating. Okay, so I can say that's equal to 0, so equals to 0, my summation of my forces in the y. So the forces in the y that I have to sum here, I'm going to start with my positive forces first. It just means add all the what's, all of these up. Okay, so I've got my force normal is pointing up. Add my force pull in the y. And my force weight is acting down, so it is negative. Right, that got a little crazy there. Alright, now I'm just going to keep it as variables for now, and I'll go back and add in as I go, because I actually didn't finish my x values, because if you're pulling, anytime you have two surfaces interacting and they're moving, it's going to always have a friction force opposing the motion. And they said it's moving, and they also made another clue it's moving when they told you that that was your mu k. Okay, so I'm sum my forces in the x, and set it equal to the mass times the acceleration in the x. Alright, the forces in the x are going to be the ones just this direction. Okay, so these forces, I'm going to have my force pull in the x, it's the one causing it to move, and my frictional force is the one opposing the motion. Now the second that the pull overcomes the friction, it's going to start moving, but that was static friction, right, before it moves. Now that it's moving, this is opposing this. If these two forces are the same, it is not accelerating. It can either be stopped or it can be constant velocity. Okay, but if this force is bigger, so if the force pull is bigger than the friction, then it's going to be accelerating in that direction. And that is what's happening. They told us that we need to find the acceleration, and they told us their frictional value there. So let's set that equal to our forces. So our forces in the x are a positive, again we say positive to the right, are a positive force pull in the x plus a negative kinetic friction, and we're going to set that equal to the mass 35.0 kilograms times the acceleration of the x. That's what we're going to solve for. Okay, and currently I've got a lot of unknowns and it might feel that way, but let's just keep plugging in what we know. I didn't resolve my vector yet, so I'm going to go up and do that really quick. Remember SOHCAHTOA. Alright, and cosine for my adjacent, sine for my opposite. So my adjacent is my x, my opposite is my y. So cosine of 25 times 185 means my force pull on the x is going to be about 168 newtons. Now sine 25 times 185. I'm going to have a force pull in the y of 78.2 newtons. I'm keeping 3 sig figs here. Alright, so now I can plug in these values that I know. My force normal isn't as simple as just being the force weight because of that force pull up. My force weight I can find, however, because it's just your mass times gravity, so 35.0 kilograms times 9.81 meters per second squared. So my force weight, 35 times 9.81, 343 newtons. Okay, just so I don't forget, it's getting kind of busy up there. Alright, so I can plug that value in. So I'm going to say, I'm just going to flip these around so it makes a little bit more sense. My force normal I don't know yet, but if I add my force pull in the y, which I do know, my force pull in the y is that upward 78.2 Newton force. Okay, that's that one and that one. Now I'm going to add a negative force weight. My force weight was 343, so negative 343 newtons. Alright, and that's equal to 0. Since this is a negative, I can add it, 343 newtons. Add 343 newtons. Okay, that's gone. So now I have my force normal plus 78.2 newtons is equal to 343 newtons. I'm going to subtract 78.2 newtons from both sides. And because it's addition, I have to subtract. So 343 minus 78.2. My force normal is 265 newtons, which is awesome because I can use that over on this side now. Nope, I gotta get out of the way there. You guys aren't here to shout at me. Okay, my frictional force, remember I can solve that using one of the equations I had. I know that my kinetic friction is equal to my force normal times mu k. Okay, I have mu k given to me, and I just found my force normal, so my kinetic friction is equal to 265 newtons times, times 0.27. Again, mu k is one of the very few values that we have this entire year that doesn't have a unit, and it's because it's a ratio. So my frictional force is 71.55 newtons. Now we have to put it back into this equation here. Okay, so that was just to find the kinetic friction. Now I'm going to rewrite this and plug it in. So my force pull on the x was 168. I'm saying to the right's positive, to the left's negative. So 168 newtons plus a negative, because friction is opposing it, is equal to my mass times acceleration in the x. Alright, so I'm going to take 168 minus 71.55, and I get 96.45 over on this side, and then because this is multiplication I have to do the opposite, which is division, so I'm going to divide by 35.0 kilograms. Okay, and I wanted to show you the units. So when you took this minus this, your unit became newtons, but remember newtons is kilograms times meters per second squared. So when you divide that by mass, your unit comes out to be meters per second squared. So my acceleration, I'm just flipping these around guys, is equal to, my calculator says 2.75 yada yada, so 2.75 Those are 3 sig figs. I think I had that rounded in the one that I did at the school, so then I didn't have any more than 2 sig figs, so I'm just going to stay consistent here with 2 sig figs, 2.8 meters per second squared. I'm fine with you guys keeping it on your calculator and then coming up and being like, oh, mu k is 2, I'm going to use 2. That's fine too. Okay. That is the final answer for that one. And remember, it's acceleration is a vector quantity, so you could say to the right or up the ramp or whatever it may be, or in the positive direction. All right, that was number 1. All right, number 2. I need to make dinner, so I need to do this one quick. All right, number 2. Actually, I'm going to do number 2 after dinner. I'm going to stop this.